This is Professor Frampton for Physics 310. Hope you guys are having a great start of the semester. If you have any questions or admin problems or anything, please either email me or contact me on Canvas. I'll try to take care of it as soon as possible. Any other questions, please refer to the syllabus or contact me. Otherwise, let's jump into it. So the first lecture is about science. So what is science? There's been a lot of questions about this, and I don't think we're going to get into exactly what science is. There's a whole science of philosophy or philosophy of science. That is an ongoing subject of research. But for us, what is science? So science is essentially revolves around experiment and measurement. That's a test in science. And there's all these different things like chemistry, and it looks like this is measuring some brain waves. This is a rocket. This is a machine in medicine. This is a physics experiment called Stern-Gerlach. I don't even know what this is. So when we associate, what we associate with science is measurement and experiment. So why is that? An example of an early scientific measurement would be Eratosthenes. I don't really know how to pronounce that. And he was able to figure out the size of the Earth, meaning radius or diameter, just by using a vertical pole at different latitudes on Earth. We don't need to get into exactly how this was done, but with a stick, he was able to put it into the ground at different places on Earth. I think it says one was in Alexandria and one was in Cyrene. I don't know how to pronounce that. And comparing the shadows at the same time of year at the different locations, he was able to figure out a pretty good approximation for the size of the Earth. That's pretty incredible. So in this case, the science is doing the measurement itself. So what is the scientific hypothesis? What does the scientific process begin with? We start with a scientific hypothesis. And a hypothesis is, well, I'll just read it from here. A tentative explanation for an observation, phenomenon, or scientific problem that can be tested by further investigation. So hypothesis is scientific if let me rephrase that. A hypothesis is scientific if there is a test experiment measurement to prove it wrong. So there's a lot of debate about what science is, but I think this is the essential feature of a scientific hypothesis, is that there should be an experiment out there to show that it's wrong. We don't necessarily have experiments to show things are correct, but we do need experiments to show that things are wrong. So let's see this. Which of these is a scientific hypothesis? Remember, we need to show that it can be proved wrong by an experiment. So here's one. The moon is made of green cheese. Well, we can go to the moon and scoop up a piece of moon and then test what that's made of. And if it's not green cheese, then we can prove this wrong. So that is a scientific statement, I think. We'll check the answers in a second. Atomic nuclei are the smallest particles in nature. Well, if we keep looking for particles and we find something smaller, that can be falsified or shown to be wrong. So I think that's a scientific statement. A magnet will pick up a copper penny. Well, we can get a magnet, we can get a copper penny, and see if the magnet picks up the copper penny. And if it doesn't, well, then we've proven it wrong. Cosmic rays cannot penetrate the thickness of your conceptual physics textbook. Well, if we have a textbook and we put a detector underneath the textbook, if it completely blocks the cosmic rays, then it may be true, but if we put a detector underneath there and we do detect a cosmic ray, then this statement is false. So that is also a scientific statement. So I think the answer is everything. Yeah, all scientific hypotheses here. All the statements here are scientific hypotheses. So this question is, which of these is not a scientific hypothesis? So protons can carry electric charge. That sounds falsifiable. Undetectable particles are some of nature's secrets. That sounds not falsifiable to me. Since we can't detect them, there's nothing we can do to falsify anything about them. So that sounds non-scientific to me. Charged particles bend when in a magnetic field. That sounds falsifiable to me because we can get charged particles and we can get a magnetic field and we can test to see if they bend. And D, I don't think they all are. I think B is incorrect. I think B is correctly not a scientific hypothesis. That's right. Okay, so the essential feature of these statements that are scientific is that they are falsifiable. And it's interesting, there's a lot of flat earth theorists out there, and they actually make a scientific claim that the earth is flat. And I have seen some YouTube videos where a person who believes in flat earth actually does an experiment and shows that their scientific hypothesis that the earth is flat is actually wrong. So in some sense, flat earthers are doing science in some way, and they can get experiments and show that their hypothesis is incorrect. So kudos to flat earthers, I think. So there's a couple things here that we should go through. Like a scientific law is a hypothesis that has been well tested and not contradicted. So it's a hypothesis that we've done experiment after experiment after experiment after experiment, and it keeps showing not false, not false, not false. So we start to believe that it may actually be true. A scientific theory is a synthesis of well-tested hypotheses. So we have a bunch of hypotheses that are well-tested, shown not to be true, shown not to be false a bunch of times. We bring it together and we create that, mix it into a theory. So important is that assumptions are foundational to any theory. Could be a strength if the assumption is itself testable, and could be a weakness if untestable or philosophical. So good examples of assumptions in science would be, we value evidence in science. And it's hard to present evidence to show that you should value evidence. Or we use logic in science. It's hard to come up with some logic that shows that someone should be logical if you don't believe it beforehand. So experimental evidence and logical consistency, these are assumptions built into science that we all just have to believe. So sometimes we could debate whether assumptions are good or not. Sometimes assumptions can be shown not to be assumptions at some point, which could be good through thought. So science is this ongoing process of understanding the world and understanding what's a hypothesis, what's a theory, what can we test, what new technology is coming online to figure all this stuff out. We should talk about honesty and dishonesty in science, because science is made up of people, and people can be honest, dishonest, and everything in between. And there has been some high-profile cases of just straight scientific fraud in the news recently. And so what are some kinds of dishonesty in science? Well, straight up lying, misleading, fabricating, suppressing data, that's a big one, stealing data from another group, plagiarizing, yes. So all of these can be, it happens because science is made up of people. And what pushes a scientist to dishonesty? Well, funding, fame, pressure, laziness, ideology, all of that. We understand that if money's on the line, there might be some pressures to falsify data or do something dishonest. When somebody have the trappings of fame, absolutely. So all of these are in play with science, and science is not perfect because it's made up of people. So what motivates the scientist to be honest? Well, personal character, high standards of accountability. Other people need to replicate experiments and try to disprove theories, so scientists keep each other honest. And there are consequences. If a scientist is found to be lying, then sometimes they can lose their job and their reputation, and that's a strong motivator. Okay, so let's talk about methodological naturalism. And this is the primary philosophical system used in scientific study. So there's some assumptions. We talked about assumptions. No miracles. All things can be explained in terms of natural processes, as opposed to supernatural processes. This distinction between natural and supernatural, sometimes a little wishy-washy. Maybe something is supernatural when we don't understand it, but once we start to understand it, we call it natural. And it seeks physical explanations for physical processes. It's not necessarily tied to any kind of religious thing. It's just a process for understanding how the world works. So some strengths is it gives us a guide for studying the universe as it is, but it sometimes has questions that may not be answerable, or seem beyond the scope of what science is. So that's ongoing conversation between people. So specific science, of course, we're doing here physics. This is the study of the physical universe. It's the basic science. That means it's the simplest of the sciences. It's not trying to explain life or economics or sociology or biology, these really complex things. It's trying to get to what is, on its simplest level, how does the universe behave? So that includes mechanics, heat, sound, electricity, magnetism, light, atomic, nuclear relativity, and all these other things. And we try to simplify the experiments as much as possible and try to get to the foundations of what's going on. So that's physics. And obviously, I think people associate physics with math. What the heck is math? And math is symbols and operations and relationships, and it's all shown, written down on a piece of paper. So equations clearly express relationships between quantities. So if we have something like temperature and pressure and number of particles, can we multiply them together? Can we add them together? And how do they relate to one another? And we use math to show these relationships. And these equations, like this person has Schrodinger's equations tattooed on their back, we can see relationships between different quantities on his back. And so the math and its sets of rules that come with math can be used to write succinctly down relationships between physical quantities. So we're going to use math to describe relationships between all of these things. Okay, so what's the ultimate goal of physics? It was to come up with the GUT, the grand unified theory. Some people think we're close to one. Some people think it's very far away. We're not sure. There's all kinds of debates. You can go on YouTube. You can go on, read any kind of news, scientific news, and this often pops up. Are we close? It's beyond my pay grade, that one. Okay, here's some questions. Although physics may be the most difficult science course in certain schools, when compared with fields of chemistry, biology, geology, and astronomy, it is the simplest, still the hardest, the central science, simple enough, but only for especially intelligent people. I think it's A, the simplest. There was a good quote by a physicist, John von Neumann, who said, people think physics is hard, but that's only because they don't understand how complicated the real world is. And the world around you, if you just look around, it's super complicated. You got people, you got life, you got the earth, you've got literature. It's super complicated. And physics is trying to get rid of all that noise and do the most basic things possible. So the simplest. Okay, let's do some more. Science is an organized body of knowledge about nature and also a guide to improving human behavior. That doesn't sound like science. Recipe for avoiding conflicts. That doesn't sound like science. Process for finding connections in nature. That sounds like science. A handbook for establishing truth. Sort of, but probably not a handbook. I'm going to go with C. Yep. Eratosthenes, I don't know how to pronounce it, made measurements to calculate, well, we know the size of the Earth. That was at the beginning. A person who says that that's only a theory likely doesn't know that a scientific theory is. Well, we learned that at the beginning of the lecture. Guess that involves many facts? I don't think so. Hypothesis of sorts? I don't think so. Vast synthesis of well-tested hypotheses and facts that have never been proven wrong. That sounds like a theory. Guess that may or may not be factual. I don't think it's that either, so I think it's C. Typically, I think people in everyday language use the word theory as if it's a hypothesis. What they mean is, when they say that's only a theory, what they really mean is that's only a hypothesis. So it's C. Scientific hypothesis can be disproved with one reproducible experiment. That sounds right. Disapproval of other scientists, many tests by many scientists, philosophical reasoning. Well, it can be disproven by many tests by many scientists, but all it needs is one experiment showing that the hypothesis is false. I think that's right. A strength of science is that scientific theories are fixed. Well, that's not true. We change them all the time. Can change with new data. Yeah, that's important. Our hypothesis of brilliant people, that may or may not be true. Are verifiable? No, they need to be falsifiable. So I think this is the important thing about scientific theories, is that they can change with new data. Difficult to change them with new data because they're well established and have never been falsified, but they can change. And that's it. That's for lecture 1. I'll see you guys next time for lecture 2.